This is Unit 16, Tropical Cyclones and Hurricanes. So we'll be focusing on some of the planet's largest low-pressure systems, largest cyclones, both in the northern and southern hemisphere. We see these tropical cyclones and hurricanes form. You're actually looking at a satellite image, sort of a photograph from space, if you will, of a very large hurricane making landfall in the Gulf Coast. This is actually Hurricane Katrina. We also had severe thunderstorms going on that day across northern Missouri and Iowa, which you can see up here in the top portion of the image. Obviously, most of your attention is drawn to the very strong storm, and we are going to learn a little bit about the mechanics of hurricanes today, their origins, some of the ingredients necessary for the formation of hurricanes, and also how they influence humans. Probably the most notable hurricane of our lifetime would be Hurricane Katrina in 2005. Hurricane Katrina is still this country's costliest natural disaster in terms of loss of both human life and economic loss, so kind of rated in dollar signs. You can see here on the afternoon of August 28th, 2005, Hurricane Katrina was essentially at peak intensity. It was churning across the Gulf of Mexico. So here we have southern Louisiana, we have southern Mississippi, southern Alabama, the panhandle of Florida, kind of all shown in this geographical region. Smack dab in the center here, we have Hurricane Katrina. The eye of the hurricane is very well seen on this particular satellite image. We have some reds and some yellows and greens away from the center. It's basically kind of showing you the intensity of the hurricane, and we talked a little bit about this when we talked about Stefan Boltzmann's law, that essentially what we're doing here is creating a false color image. And so actually the reds and the blacks on the map are where the cloud tops are the highest, and the temperatures are therefore the coldest. And we know as we go up in the altitude in the troposphere, the temperatures decrease. So the reds and the blacks are actually colder than the surrounding air temperature, and so you're seeing the image show you that that's where the actual strongest activity is. If you were to put the legend on here, you'd see that these are indeed the coldest temperatures. And again, in order to get cold temperatures, you must have a cloud that's very high up in the air, and if it's very high up in the air, it's probably stronger than the storm next to it. So it's kind of how we judge or base intensity in some of these hurricanes. The temperature at the center of the hurricane is actually just measuring the temperature of the Gulf of Mexico. So there's no clouds. It's the beam is measuring straight to the surface of the ocean. In this case, the surface of the Gulf of Mexico. Over here, there's no clouds in the way, so we're measuring the surface of the land over Texas and over other portions of the Gulf of Mexico. So this satellite imagery, which we're going to learn a little bit more about in Unit 17, our last unit, is going to focus in some of these satellite and sensing techniques. But for today, we're going to focus on these very large low-pressure systems that meet a certain space and time criteria and also have a certain wind speed threshold that they must be categorized by. You can't really talk about hurricanes and tropical cyclones in any sort of introductory to weather class without talking about the 2005 hurricane season. The 2005 hurricane season was very active, as you can see here in the bottom right image. Each one of these was a separate track of a different hurricane. They're color-coded by their intensity, so the magentas here are at storms that were at or above Category 4 status. On the Saffir-Simpson scale, which we'll talk a little bit more about in a bit, we had 26 named storms, 13 hurricanes, 7 of those considered major hurricanes, Category 3 or above. That year we had an unprecedented 4 storms that reached Category 5 status on the Saffir-Simpson scale, the highest or the most damaging, destructive category that we can rate a hurricane. At one point we had Katrina and Hurricane Rita forming at the same time in the Gulf of Mexico. You can see here Gulf monsters in 2005, Katrina and Rita both present, 2 very intense, strong hurricanes, almost creating what we call a Fujiwara effect over one another. Katrina formed on the afternoon, or Katrina was most intense on the afternoon of August 28th, and you can see the superimposed satellite image of Hurricane Rita on September 21st. And I invite you to visit this URL here at the bottom. This is an animation or a loop of all the hurricane activity from satellite in 2005. And it's a really interesting animation that kind of shows you the storms as they progressed. So a little bit more about tropical weather in general. Tropical weather is weather that occurs between the Tropic of Cancer and the Tropic of Capricorn. So we're focusing in on the region between 23.5 degrees north and 23.5 degrees south. In this general area of the globe, we don't have any major air mass differences. It's all hot and muggy air. So we don't have fronts in this portion of the world, and we really have we don't see air masses with differing temperatures at all. It's all kind of 80 and sunny and lots of humidity all the time. And if you've been to tropical regions, you know this. From global circulation, we know that the trade winds blow in an easterly fashion in these tropical regions. So if you were in the area 30 north to 30 south, you would expect an easterly wind or weather to progress from east to west in your area, which is opposite of what we experience here in Chicago. The very intense solar heating causes lots of convection, thunderstorm activity due to daily heating. So if you live in the tropical regions, you know that every afternoon you're at the risk for isolated thunderstorm activity. We do not see four seasons in the tropics because we do not have large air mass differences. We always have a lot of incoming solar energy, and it's always kind of the seasons are rather being marked by temperature are instead marked by differences in precipitation. So in the tropical regions, it's not spring, summer, winter, fall. In the tropical regions, it's the rainy season and the dry season. Typically, we don't see large differences in temperature, but we do see differences in precipitation, depending on the movement of the ITCZ, the Intertropical Convergence Zone. A hurricane, by definition, is an intense low-pressure system with tropical origin. It has to have winds sustained at 74 miles per hour. So if the winds are not at least 74 miles per hour, we do not have a hurricane. We probably instead have a tropical storm. We'll go over the intensity scale here in just a second. Hurricanes are essentially heat engines. This is totally different than mid-latitude cyclones. Mid-latitude cyclones feed off of the differences in air masses. Hurricanes feed off the fact that the air is just really warm and it's all the same. It has a lot of moisture content. So hurricanes feed off of the release of latent heat from condensation, shown over here in number 4. So as water changes phase from a vapor to a liquid, condensation, we know that releases more heat in the atmosphere, making the air even lighter, and it continues this convective process. Until all of that heat and humidity is used up, the hurricane will continue to thrive. The main purpose we have hurricanes on this earth is to transport this excess tropical heat and moisture to the mid-latitude regions. So these hurricanes will often curve away from the tropics in either a north or a south fashion to sort of transport this energy away. And there is no difference at all between a hurricane, a typhoon, or a tropical cyclone. All of those are the same thing. It's just depending on what basin the storm forms in. If the storm forms in the Pacific Basin, specifically the Eastern Pacific Basin, or forms in the Atlantic Basin, we give it the term hurricane. If it forms in the Indian Ocean or South Indian Ocean, we give it the name tropical cyclone. If it forms in the West Pacific, we give it the name typhoon. So all of these are essentially scientifically the same thing. There's no difference between a hurricane and a tropical cyclone. It just depends on what basin, ocean basin, that these are forming in. Just like severe weather needed moisture, instability, lift, and wind shear, we must have certain conditions favorable for the development of tropical storms and hurricanes. In order to achieve a hurricane, it's pretty black and white. The water temperature must be at least 80 degrees Fahrenheit. If the water is not at least 80 degrees Fahrenheit, you will not get tropical cyclone or hurricane development. We need some sort of convergence. If there's not convergence of the air, we get no lift, and if we get no lift, we have no convection, and we get no thunderstorms, which are the precursor to getting hurricanes. So there must be a little bit of convergence going on. Typically, that convergence is provided by the ITCZ or some sort of low-pressure wave that moves out of Africa. We call those African easterly waves. They're low pressures or disturbances that move over Africa. They come into the Atlantic Basin, and then they curve towards the United States. Notice this image here over on the right. This is global hurricane climatology. There's never been a hurricane close to the equator. So 5 degrees north to 5 degrees south, we've never had a hurricane. The reason for that is need some Coriolis force. Recall from our forces in wind lecture that we talked about the Coriolis force is 0 at the equator. If there's no Coriolis force, there's no mechanism for the air to begin to rotate or move in a circular fashion. It has no vorticity, no spin. We need some Coriolis force in order to get the air rotating. Okay? Once you get north of 5 degrees north or south of 5 degrees south, you have enough Coriolis force for the genesis of tropical cyclones and hurricanes. This is finally one last thing that we look for tropical cyclone activity is very weak upper level winds. That is totally different than severe weather. Remember from severe weather we like the jet streams. We like the wind shear to be very fast. We like the winds to be increasing with speed and direction with height. Having the wind shear necessary provided the separation from the updraft and the downdraft in a thunderstorm. In a hurricane, if we have very weak upper level or strong upper level winds, it tears the hurricane apart. Hurricanes do not like vertical wind shear. Instead, they like very weak upper level winds because weak upper level winds will not disrupt the organization of the storm. If you look at the climatology of where hurricanes are forming, we typically see more hurricanes with a La Nina event, fewer with an El Nino. El Nino and La Nina, you skipped over this in your Weather Studies Investigation Manual, but El Nino and La Nina are essentially states of the sea surface temperatures in the Pacific Ocean. It's not too important for introductory students to understand El Nino and La Nina, but if you ever hear about El Nino and La Nina, they typically do influence the frequency of hurricanes every year. The most active basin is the Western Pacific. Those are typhoons. On average, they experience about 16 typhoons every year. The Atlantic Basin typically has about 5 hurricanes per year, max being 12. We've had several maximum size hurricanes. 2005, again, had 26 named storms, 12 hurricanes, 4 of those being Category 5. Globally, we see an average about 45 storms of these tropical cyclones every year. So let's focus in on the idea of the Atlantic Basin, what we're familiar with here in the United States, which are hurricanes. Hurricanes go through a set of staged birth to death, just like thunderstorms and just like mid-latitude cyclones. Okay. As we progress here from 1 through 4 in this number scale, the intensity of the storm is essentially just getting stronger as we go down. So the birth of these sort of hurricanes is what we call a tropical disturbance. A tropical disturbance is nothing more than a mass, an amoeba, if you will, of thunderstorm activity that has a very slight cyclonic rotation. So in the northern hemisphere, it would have a very slow sort of counterclockwise rotation. It's nothing more than a mass of thunderstorms. There's no eye wall, there's no eye of the hurricane, there's nothing that resembles, you would not look at a satellite image and go, wow, that's a hurricane. Right? It's just kind of a clump or a glob of thunderstorm activity. If that glob of thunderstorm activity begins to strengthen, it might be classified a tropical depression. Tropical depressions are when we see a couple closed isobars appear. So instead of just a ripple in the pressure field, we instead see a couple closed off circles of isobars. Recall that isobars are lines of constant pressure. So if you're looking at a sea level pressure map, you might see a couple of closed contours. That's a good indication that we might have a tropical depression. Tropical depressions, by definition, must have winds between 20 and 34 knots. So it's basically just a tropical disturbance that's getting a little bit stronger. At this point, the National Hurricane Center will give it a number. Tropical storm number 5, tropical storm number 15. We give those a number at the tropical depression stage. If the tropical depression is forecast and continues to strengthen, it may become a tropical storm if it has wind speeds greater than 39 miles per hour, but not exceeding 73. Okay, so in that realm of 39 to 73, we give that a tropical storm status. It will now have several closed isobars. The pressure will be dropping, meaning the storm is intensifying. At this time, the National Hurricane Center will give it a name. Tropical Storm Debbie, Tropical Storm Mary, whatever it might be, the storm will get a name, and if it is upgraded to a hurricane, it will keep that same name. Okay? A hurricane is just a strong tropical storm, so we achieve that 73 or go greater than that wind speed, greater than 74 there you can see at the bottom. If you get to that 74 threshold, we now classify this storm as a hurricane. The winds are exceeding 64 knots or 74 miles per hour. The hurricane will keep its same name as before. So instead of Tropical Storm Debbie, the storm is now Hurricane Debbie. A three-dimensional structure hurricane looks a little bit different than other storms that we've studied, like the supercell, which has a rotating updraft. The hurricane actually has spiraling air around what we call the eye wall, but in the center of the eye, the air is actually descending. As the air descends, we know it warms and dries out, dry adiabatically, and so it creates this hole in the center of the circulation, an amazing feature known as the eye wall. There is outflow above the storm, so you'll see some ruggedy cirrus looking ice crystals kind of being vented out away from the updraft, but essentially here at the surface, we're spiraling in just like a normal low pressure system. The air is rising and sort of spinning out aloft. From visible satellite, the hurricane structure looks pretty cool. We have an eye here present in this particular visible satellite image right in the center. It's surrounded by this circle, which is known as the eye wall, which is the most intense portion of the hurricane. And then outward away, we have these sort of spiraling rain bands that bring with them waves of thunderstorm activity. In the upper right, we see an eye wall penetration from a hurricane hunter's aircraft through Hurricane Katrina. It's pretty amazing here. You can see, you look inside of the hurricane's eye and you look straight up and you can see clear blue sky, which is pretty cool. This is a radar animation from Hurricane Katrina when Hurricane Katrina made landfall in the afternoon of the morning of August 29th, 2005. At this time, Hurricane Katrina was actually downgraded to a strong Category 3, so this was not even a major category, or this was not a significant hurricane at landfall. It actually was rapidly weakening when it made landfall in New Orleans and still caused the most destructive storm surge ever recorded in history. You can see all the precipitation here, but generally you can just see the spiraling of the rain around the center. The eye at this time was actually probably passing right over New Orleans. We had significant storm surge to the right of the track. You can imagine if the storm is spinning like this, it's shoving water up against the coastline in places like Gulfport and Biloxi, which experienced damaging storm surge from Hurricane Katrina. Hurricane Katrina at this point was beginning to weaken. If you look here on radar, you can see this very fine line of blue kind of wrapping into the eye of the center of the hurricane. That is actually some dry air that is wrapping in and helping to kind of combat the saturation of Katrina. It's unsaturated air being wrapped in, and so it's beginning to make Katrina weaken. There's the link to the YouTube video if you want to watch a little bit about Hurricane Katrina and its landfall, but here it is at peak intensity, and really honestly folks, when you take a look at a hurricane, you can tell it's intense if the eye wall is symmetrical. So I take a look at the eye. If I have a beautiful symmetric circle that almost looks like it was drawn by a computer, there's a pretty good chance that that storm is a very significant storm. At this point in time, Hurricane Katrina was at Category 5 status on the Saffir-Simpson scale, and the eye is almost looks like a jelly donut. The eye is just perfectly symmetrical. When the eye is perfectly symmetrical, I call this the hurricane has essentially reached what we call a steady state, and it's really comfortable in what it's doing. It's processing that heat and moisture, it's transporting it northward, and it's kind of just doing its job at this point. Official hurricane season starts on June 1st and goes through November 31st. During those times of the year, the Atlantic Basin is favorable in different regions geographically for the formation of hurricanes. You can see in June it starts out a little bit further south in the Caribbean, and by July a lot of the water is favorable, and specifically August, but by September the entire basin is really favorable for the development of hurricanes. If you're watching this in the fall semester, it's very likely that you're probably watching this lecture and either we have had a lot of hurricane activity or there is currently sort of tropical activity ongoing in the Atlantic Basin. If you're watching this in the spring, that's probably definitely not the case, as hurricane activity really doesn't start ramping up until June and July. By October, the shallow water of the Gulf of Mexico has really started to cool off and is not at that 80-degree threshold anymore. The deeper water in the southern Caribbean and the Atlantic are still very favorable, though. We have had storms sustain themselves into November and even early December if the water conditions in these deep waters of the Caribbean and the Atlantic can maintain favorable. But in general, you can see the storm track or path by November is not to make landfall in the United States because the water is too cold. Instead, these storms kind of track more of a north and east fashion. If you like probabilities and you like odds, the annual probability of having a named storm at different portions in the basin is very high. So if you're focusing on the Gulf of Mexico, there's better than a coin flip of a chance that there will be a named storm in the Gulf of Mexico every year. Basin wide, you can see kind of the favorable, the sweet spot, if you will, the hot spots for development are just east of, basically you get out east of Cuba, the Lesser Antilles, the islands out here. That's a very favorable area for the genesis of a storm. Oftentimes those storms will kind of hook up towards the Bahamas, or they will take a more southern track just south of Jamaica through places like Cuba, and then they'll get into the Gulf of Mexico and potentially influence Mexico or the southern United States. Hurricanes weaken when you take away their ingredients that are necessary for formation. So if it moves over water that is less than 80 degrees Fahrenheit, they will weaken. When they move onto land, you cut off the moisture source, the heat engine, essentially, if you will, that the hurricane is feeding off of. Not only does it cut off the moisture source, but when a hurricane moves over land, it begins to experience increased friction due to the trees and the buildings, which cause the circulation to kind of spin down a little bit. Hurricanes will also weaken if they move into areas with very strong wind shear. So hurricanes can get caught up in the upper level westerlies and the upper level jet stream and kind of be sheared away or torn apart and weaken that way. So again, official season is June 1st to November 31st. Most of the hurricane activity, though, comes in August, September, and October. And in fact, take a look at this graph. This is pretty amazing. Let's focus just for a second on the red curve. So this is the annual cycle going throughout the year. We start to see hurricane activity on average starting in May, maybe even in June. By July, we start to increase. August is really our ramp-up month. And the first 2 weeks of September are really responsible for a majority of peak of the hurricane activity. We begin to decline, but we still have a lot of activity until mid-October before things begin to quiet down. 80% of all hurricanes come in the months of August, September, and October, which is probably kind of weird to you because if you think about the Northern Hemisphere solar cycle and you ask yourself the question, when is the longest day of the year in the Northern Hemisphere? The longest day of the year is June 21st. That's when we have the most amount of incoming solar radiation. Why does June 21st not correspond with this idea of peak hurricane intensity? And the answer to that is because we have a very large lag effect. Recall that the oceans are very, very large. They have a lot of mass, and the water has a high specific heat. So it takes the water a really long time to get up to that 80-degree temperature threshold that we need. And when we do achieve it, it lasts for a pretty long time. When you heat water up to a certain temperature, it will hold its temperature for quite a long time. We know things become favorable around June, or the most incoming radiation is happening on June 21st. But it takes almost 2 months for that ocean water to continue to heat up and heat up and heat up with the surplus of energy before the peak temperatures in the Atlantic Basin are met, and that happens again on or about the first week of September. Hurricanes are named fairly easily when they achieve tropical storm status. Again, they receive a name. They will keep that name through hurricane status. We did this, we've been doing this throughout history just to make storms easier to identify, make public awareness sort of campaigns, but also for meteorologists it makes tracking these storms a little bit easier. In 1953, the National Weather Service started using female names to name all storms, and they decided that's probably not a good idea. We shouldn't just use female names. That's kind of rude. We'll start to throw male names in. In 1978, they began to use both male and female names. If a storm causes damage that is especially notorious and would cause insensitivity, we basically change the name. We retire the name. So, for instance, there will never be another Hurricane Katrina. There will never be another Hurricane Andrew. There will never be another Hurricane Sandy. These are storms that have had a significant impact in lives, property lost around the country. Naming another storm Hurricane Katrina would be rather insensitive to those folks that were living through Hurricane Katrina. So if a storm is notoriously deadly or costly or has a significant impact, the National Hurricane Center, which is based in Miami, Florida, will retire the name of that storm and replace it with another name. So here's the kind of just a list of rotating names. You'll see some names on here that have now since been retired. Sandy has been retired since this. Let's see, Katrina was on this list in 2005 and was replaced by Katia. And so if you see your name up here, there's a good chance that's cool. I mean, you could achieve, you could have a hurricane named after you, but if you don't see your name, it might just be because that storm has been retired. Every 6 years, the list will rotate. So after, for example, in this particular example, in 2006, we had this particular list. In 2012, we'd have that same list again. So you have a chance every 6 years to basically get your name. And so every 6 years, I always root for a very active hurricane season. I'm always hoping for a Hurricane Victor. It's not going to happen. I need a 2005 like year if I'm ever going to achieve a Hurricane Victor. So if you're at the end of the alphabet, it's a little bit harder to do. However, it is certainly possible, as the year 2005 showed us. Okay, what's the talk about all this Saffir-Simpson scale deal? The Saffir-Simpson is the intensity scale that we use to rank hurricane activity. For tornadoes, we had the Fujita scale. For hurricanes, we have the Saffir-Simpson scale. The Saffir-Simpson scale is based on a category from 1 to 5, so it's kind of similar to the Fujita scale. But unlike the Fujita scale, which is based on damage, the Saffir-Simpson scale is based on central pressure of the hurricane. The lower the pressure, the greater the category, because we know if the pressure is lower, the pressure gradient must be greater, and therefore the wind speeds must be greater. So if we see a very sharp drop in the central pressure of a hurricane, when you look at a surface weather map, there are going to be isobars that are very tightly packed together. And we know where we have isobars very tightly packed together, we have very strong wind speeds. So we can categorize these storms based upon their wind speed and their central pressure, because remember, hurricanes last for a much longer time than tornadoes. Tornadoes, we're talking about minutes, hours at the most. Hurricanes are lasting on the order of days, maybe even weeks. So we have time to get out there and drop probes and fly hurricane hunter aircrafts into these storms and take accurate scientific measurements of the properties that we're interested in. And in some ways, the Saffir-Simpson scale is a little bit more scientifically oriented than the Fujita scale, which is kind of just based off of sort of a subjective assessment of damage. Inside of a hurricane, we can have several different destructive elements. One of them being very fast wind speeds, like Hurricane Andrew, which caused $30 billion in damage to South Florida. Hurricanes like Floyd and Mitch have produced significant flooding. In fact, Hurricane Agnes in the early 1970s dropped 19 inches in one day across portions of Pennsylvania. And in fact, we see that inland freshwater flooding is the most deadly aspect of a hurricane activity. It's not the tornadoes that are spawned. It's not the high wind speeds. It's the inland freshwater flooding. Way more deaths than any other sort of weather-related fatalities or weather-related disasters. Inland freshwater flooding is responsible for so many fatalities per year. People think they can drive through the flooded roadways, and it's not true. In the case of Hurricane Katrina, widespread flooding caused rapid transport of bacteria and waterborne illnesses that also caused fatalities. So inland freshwater flooding is something to be very serious about. Also, things like storm surge. We're going to talk about each of these destructive elements, but I'll just introduce here storm surge to you. This is a rapid rise in water. We've had several documented instances of storm surge killing several people, including Hurricane Katrina. Take a look at this, though. 1900 Galveston, Texas storm. 6,000 people were killed due to storm surge from a hurricane. Tornadoes also form from hurricanes, a lesser-known sort of fact. They're often not strong, but they do form, and they are very common with landfalling hurricanes. Let's take a little bit more of an in-depth look at each of these destructive elements. Storm surge, in particular, is dependent on the geography of the region. In the upper left, we have storm surge as denoted by a coastal region that is very shallowly sloped into the water. So this is we call this the bathymetry of the coastline. We ask ourselves, how shallow is the water X amount of feet away from the normal shoreline? And you can see in the upper left, this is just a very gradual slope into the ocean. And on the right-hand side, we have this very sharp cutoff, this very sharp drop that actually does not or is not as favorable for a storm surge. When we have these big pushes up in water, it doesn't react the same way. Storm surges on a shallowly sloped coastline cause the water to simply pile up, pile up, pile up. There's no barrier. And you can see here in this image in the bottom left, this is storm surge in 2005 from Hurricane Katrina. And you can see that the water was just building up and building up and building up, and all of a sudden it's sweeping away homes due to this rapid rise in the water activity. Here's another image from 2005 of Hurricane Katrina. This is where Lake Pontchartrain crested the levees due to storm surge. You got to remember, in a place like New Orleans, that is at or below sea level in most places of the city, that levees were built around these, and the purpose of a levee is to keep water out. Okay. Well, when water gets in the levee or breaches the levee and then fills up the town, it's very hard to get the water out of the city. You have to physically pump it out over the levee. And so when we had the levees fail in the lower Ninth Ward during Hurricane Katrina, we saw a rapid rise in water. In fact, you can see some homes here. This is actually the top of a home shown right here. This is, most of these places were under 12 feet of water. They're at 12 feet below sea level. The water breaches the levees and basically fills up like water in a bathtub. Wind speed can be very destructive, especially to the right-hand side of the path of movement. So in this image, we have a hurricane moving from the south to the north, towards Alabama in this case. You will always find the greatest amount of wind damage on the right-hand side of the track. The reason for that, the storm is moving to the north, and we have the wind over here also moving to the north. So we add the two vectors together, and the net wind is much faster than the net wind on, in this case, the west side of the storm. We have the storm's movement. We subtract away the fact that the wind is moving in opposite direction. So we have vectors kind of working against each other over here. On this side, we have the hurricane's movement plus the direction of the wind, and the swath of greatest damaging winds is usually just to the right of the eye wall. These are pictures from Hurricane Andrew in 1992. We had 2x4s piercing palm trees and 3/4-inch plywood that was basically thrown like needles through trees. So you will always get this greatest storm surge and greatest sort of wind damage on the right flank of the storm, the lowest on the left. So this is relative to the motion of the storm. So if the storm is moving due north, you'll always kind of get that to the right. If it's moving this way, you'll get it to the right still. So always just kind of focus on to the right of the path of the storm. Hurricanes can also generate rip currents. They can suck you out if you're not a good swimmer, or even if you are a good swimmer. These large waves that can arrive days before the hurricane reaches your location. Oftentimes, there are several fatalities with each landfalling hurricane due to the fact that rip currents can kill people. I mentioned that tornadoes can be spawned by landfalling hurricanes. This is a climatology of where tornadoes occur when hurricanes do make landfall. And you can see there is again a preference for sort of this quadrant number 1 in the Cartesian coordinate system, or quadrant number 4 for tornado activity when it makes landfall. So the hurricane is spinning in the northern hemisphere. We have this counterclockwise motion. It makes landfall. There's increased drag and friction with the new surface as it makes landfall, and we create these brief spin-ups, these tornadoes that look a little bit more like landspouts than tornadoes. They are still tornadoes. They still cause damage. Typically, they're not strong tornadoes, and they don't last very long. But there are and have been several documented tornadoes with hurricanes. You can imagine all of that air that's spinning in the eye wall. All you kind of have to do, just like an ice skater pulling her arms into the center, stretch that a little bit, stretch that spin a little bit, and you can get a tornado to form. Hurricane watches and warnings are issued from the National Hurricane Center. A hurricane watch will be issued 24 to 48 hours prior to the arrival of the storm. So you're talking a day to 2 days in advance. Hurricane watch will be posted. If the National Hurricane Center feels like an area is going to be threatened like a hurricane and the hurricane is definitely imminent, 24 hours in advance, the Hurricane Center will issue a hurricane warning, meaning you probably need to evacuate your area or take the necessary precautions to ride out the storm if you feel like you can do so. The forecasts for hurricanes look a little bit different than the forecast for tornadoes. Obviously, we do a little bit better job of forecasting these because we have a little bit of advance notice. Here is the forecast for Hurricane Katrina. This was 3 days before landfall, and you can see what an amazing forecast. We have the best guess path from the forecaster. We also have a cone of uncertainty, meaning yes, the hurricane could track anywhere in this cone. It is less likely as we get to the edges of the cone, but still possible. So we call this the potential track area, or quote unquote the cone of uncertainty, meaning the storm could make landfall anywhere inside of that cone, but the most likely location is for this storm to take the path of the black dotted line. The path, in this case, took it right over the top of New Orleans. A great forecast by the National Hurricane Center and the National Weather Service. Plenty of time in advance to evacuate folks out of New Orleans. Some of them didn't have the financial means to do so, and so there's a lot more socio-political, economic sort of considerations to take into this, especially when you consider the vulnerability of Louisiana to hurricanes, being the fact that they are below sea level. And relatively speaking, New Orleans is a very impoverished city. So when you start thinking about all of these things together, the vulnerability of New Orleans, it's very clear to see why this disaster happened, despite the fact it was a really great forecast from the National Hurricane Center. When hurricanes influence the United States, they're typically coming from these African easterly ways, so they travel easterly across from an east to west fashion, easterly wind across the Atlantic Ocean, and then they will probably either take path A, path B, or path C, depending on the strength and location of the subtropical high pressure. We call it the Bermuda High. It's really a general area of high pressure around 30 degrees north that sits over the Atlantic Ocean and kind of steers hurricanes. If the high pressure is way over here, so I take this high, I pick it up, I move it, so I'm going to pick it up and drag it way over to somewhere above the text Atlantic Ocean, you will probably get a storm that will curve around and miss the United States and take track A. If you make it strong and position the high pressure system where it is in this example, it's very likely that the storms will pass, take a southerly track, cut up through places like Jamaica, Cuba, enter the Gulf of Mexico, and maybe make landfall in Texas, Louisiana, Mississippi, Alabama, or potentially even Florida. They'll take more of a B or a C track if the high pressure system we call these steering high pressure systems because they kind of steer the direction of the hurricane, and they basically determine whether or not the hurricane will take path A, B, or C. I think you know this already, but just so we can kind of hammer this out, there are the main differences between mid-latitude cyclones and hurricanes. The only similarity is that they're both low pressure systems. That's really where it ends. They're both areas of strong low pressure. Typically, hurricanes will have a much lower pressure than the mid-latitude cyclones, but they are completely different in almost every other aspect. Hurricanes feed off of heat engines, latent heat release due to condensation. Mid-latitude cyclones have fronts. They feed off of the different air masses. Right? We have fronts with mid-latitude cyclones, no fronts with hurricanes. Mid-latitude cyclones are much larger, hurricanes much smaller. Mid-latitude cyclones have air sort of spiraling in and rising, so we have a cloudy center. We have air descending in the center of the hurricane in the eye. So we have lots of differences between mid-latitude cyclones and hurricanes. And remember that mid-latitude cyclones form in the mid-latitudes, whereas hurricanes form in the tropical regions. There has been a lot of talk, especially since the 2005 season, if climate in a changing climate was having an impact on the amount of hurricanes. Since 2005, we really saw a decrease in the amount of hurricane activity, and so some of this talk has kind of went away, but it's not gone. There is still a lot of folks thinking that climate change is related to hurricane and hurricane intensity. So the question here is, are hurricanes becoming more frequent and intense? The answer is yes, they are becoming more intense. We know that because the Clausius-Clapeyron equation tells us that if we do have increased heat and humidity, or increased temperatures of the climate, we do have an increased water vapor content. And so we know that the hurricanes will probably get much stronger with a changing climate, at least a climate that's getting warmer. But we know there are also cycles in the frequency of hurricanes. They come in about a 20 to 40 year cycle. 40s through the 60s were very stormy. The 60s to the 90s were quiet. And 1990s through to 2015 is projected to be relatively stormy. So we go through these cycles, and sometimes they last 20 years, sometimes they last more like 40 years. But we go through these sort of active and inactive periods and sort of natural variance or natural variability. We also have year-to-year variability because of things like El Nino and other ocean and atmosphere oscillations that can change or sort of change and govern the amount of hurricanes that we see. This is a bird's eye view looking down in New Orleans, especially the marshy area. In fact, here's kind of a topographic map looking straight down in the central business district of New Orleans. I just want to talk a little bit about Katrina and why it was such a disaster. I encourage you, in the Weather Studies Investigation Manual, you'll have some of these questions that kind of interrogate this a little bit more. But Hurricane Katrina, so this is New Orleans. To the north, we have Lake Pontchartrain up here, and we have the river moving through the city. And if you've ever been to the French Quarter, you know kind of this is where the location is in terms of geography. But essentially here we have this giant levee. Okay, all these purple things here shown are levees to keep water out. You can see the lowest topography in New Orleans is in the 9th Ward, specifically what we call the lower 9th Ward, which is over here where I'm circling with my mouse cursor. You can imagine that is the most vulnerable area because it is the lowest below sea level, almost 9 feet in some places. And so what do? Of course, we have the only cheap housing in here, so we force folks that are at an economic disadvantage into these governmental housing projects that are over here in the lower 9th Ward. And of course, you know, it's the most vulnerable area, and we ask those folks to evacuate, and they have no means to do so. But when Hurricane Katrina passed to the north, the wind switched around the other direction. It started piling up water against these levees. The levees could not withstand the amount of water, and the levees essentially were breached. The lower 9th Ward, which is this entire levee right here, filled up like a bathtub. And we had 15 feet of water in some places in the lower 9th Ward. And you can imagine 15 feet in your house, for most of these houses in the lower 9th Ward, meant that even if you were standing on your roof, you were probably still underwater. And so I encourage you to read more on your own about Hurricane Katrina, not only the events leading up to the event, but during the event, and especially the political and response from our federal government after this. This was a national disaster, a travesty in terms of response, forecasting this event. Forecasting the event was great. We had all of the signs that this was going to be a very bad event. The way we reacted to it, unfortunately, was not so great. So read up, if you will, a little bit more on Hurricane Katrina and how it caused this. We're seeing more and more of this type of stuff because not necessarily, you know, if you want to make the argument that climate change, you know, whatever, I think that is a secondary argument in this case. This is not about are we going to have more or less storms in the future. Certainly that is a very important consideration. We are seeing now are more and more and more of these quote-unquote natural disasters. And I hate that word. These are not natural disasters. These are man-made disasters. And we are building in areas that we choose to build in that should not be built on, quite frankly. They're very vulnerable areas. This is a great example of commercialization, hotels, beautiful homes being built on barrier islands. Barrier islands are just that. They're a barrier between the ocean or the sea to protect you from beach erosion and hurricane activity. And yet they provide the most beautiful view over the water. And so these folks are very vulnerable when these sorts of events happen. And you can imagine that we have disasters when this sort of stuff happens. But there's no reason that these folks along the shorelines should be paying the same in insurance as somebody who lives inland. They choosing to live there, they choose to take the risk, and therefore they should be paying for that enhanced risk along these coastlines. So not necessarily seeing an increase in the amount of storms per se, but we are seeing an increase in the vulnerability because we are building in very prone areas to natural disaster. Here's a great example of this. Beautiful multi-million-dollar retirement homes along the beach, right, where everybody wants to retire in your beautiful home along the beach. And yet what happens when you get a little bit of storm surge? Your home gets washed away. Okay? So we need to start rethinking land use and land use planning and where we're deciding to build not only residential homes but also commercial entities, and whether or not it's a good idea to be building in these areas that are very prone to hurricane activity. And really do the cost-benefit analysis, because when these events do occur, you essentially wipe the landscape away, and it's basically a start-over project. So If you go to coastal.eargs here at the USGS, you can see the mapping changes in the photos that are provided by the USGS. Some pretty amazing changes in the landscape over the last 50 years, especially in coastal regions. We see a lot of people like to retire and move to Florida and build buy or build their dream home on these beaches. And we're seeing more and more and more losses, but it's not due to more and more storms. We're seeing more and more losses due to the fact that we're building more and more and more in vulnerable areas. Okay, so I'll step down from my soapbox here, and hopefully you enjoyed a little bit about hurricanes. There are several videos out there. I'm going to actually post a video here after this that is a link to a YouTube video of hurricane hunters as they flew through Hurricane Katrina. So please take a look at that. It's a pretty cool sort of expose on the hurricane hunters as they fly through Hurricane Katrina, and then finish the hurricane section in your weather studies investigation manual as your assignment.